what we do with this, typically what we do, typically for quantum circuit and also. So you start from this. You start from C0 is known. Because it is your preparation. In your experiment, you are at the ground state. Typically, ground state. Okay? For a superconducting circuit, you are at very low temperature, so you are at 0 photon, no excitation. And then you manipulate your system. Okay? Then you take your experiment during time 0 t, and at the end you obtain upside of t. Okay? Following this equation. Okay? You start from T0, you take this differential equation, it is an initial value problem, okay? And you obtain psi of t. But in the experiment, your psi is just something which is a set. At the end, to see what's going on, you take a measure, okay? And you measure measurement of observable. I will say it is an operator, of course. I will say f hat. And for measurements, I know that I get some data, okay? And I know that if I repeat my experiment, okay, many times, and I consider the average value of f hat, which is what? It is psi, f hat, and psi. I can, at time t. Okay, so I do an experiment. I start from always the same thing. I know that I should finish at capital T, at this state. At the end of the experiment, I use measurement of f hat. Okay, I obtain a number. Okay, the value of a position, the value of an impulsion, and so on, the value of energy atom. I do this 2 billion of times. I take the statistic, which means I take the average value. The average value is given by this, which means that the density, the wave function, is not a position, it's something, it's a probability law associated to this. In this case, what you have is this. So either, in fact, you want to have, so you have an observable f, like this, and you want to have its average value at time t. Okay? Because it is the only things that you can get from experiment. Do the experiment many times and do a statistic. Okay? It is nothing. The wave function is not a position, is not something. It's just a probability law, which is very specific. And I want to compute this, and I want to have, so this is f at time t, people say, average value at time t, and I want to compute df, just the average value over dt, because it is something that interests me. If I do this, you do the computation because psi obeys to this, and you see it is 1 over EH, and here you have a bracket of f hat with h. Okay? Okay? Because just f is fixed, okay? And it is just this. Okay? And now if f is a constant of motion, which is its invariant, it means that it commutes with h. Classically, it takes at 0, but its average value is constant. So we have something which is a conserved quantity. In average, with respect to the statistic, okay, there is nothing more, in fact, in quantum mechanics. So psi, the wave function is a probability. And the relation between, at the end, you have all the statistics that you do, is just this, and check that if I measure this, I should have this kind of statistic. If it doesn't give me the statistic I expect from this final wave function, then there is something not going on, or my prediction is not good, or I have some problem in my experiment, or my model is not good, and so on. It's the way that you get the feedback of the experiment. Okay.
So, is it an abuse of language to put that f is a constant of motion, like the operator f, or should we maybe put that the expected value of f is a constant of motion?
It's the same.
Well,
It's a constant in average. In average, it doesn't move.
Yes.
If f of h commute with h, it doesn't change. Its average value, okay, it doesn't change. And the relation between this and this, it is related to something which is constant. Okay. So you see so this is Schrödinger, and this is Heisenberg. I will put on the web this afternoon the note of the lecture, because I have some correction to do. Some exercise for next last time. I will make the correction at the beginning of an hour. We'll finish the next session will be averaging, rotating wave approximation. That is widely used.